Hello, my name is Ravi Syaputra. I'm a student from Syaputra University, majoring in Mechanical Engineering, course 2022. And today I'm going to be discussing about the last module of MOM lab about strain measurement tests. So moving on to the data processing and answering model questions. So the first data that we're going to be discussing is the dimension data. Here, as can be seen from the picture, the specimen that we're going to be using is an I-beam, specifically a 6061T6 aluminum specimen with several parameters indicated there, as can be seen from the picture. So moving on to the next data, we're still discussing about the dimension parameter. So more specifically about the distance for a strain gauge that is installed on the side of the beam, as can be seen from the image. There's C1, C2, C3. So C1 is the distance from the bottom part of the beam to the strain gauge C. C2 is the distance from the bottom of the beam to the strain gauge EFG, or the neutral axis, and C3 is the distance from the bottom of the beam to the strain gauge D. So moving on to the next section, where I'm going to be discussing the strength versus time graph that is gotten from the data reading of the each of the strain gauge. So first of all, we have strain A, which is located at the top of the beam, and strain B, which is located at the bottom of the B. As can be seen, strain A will experience compression because the load that is applied to the beam is going upward. Therefore, strain B, in the other hand, will experience tension. As can be seen from the graph, that strain A has negative values, while strain B will have positive values there. So the same thing will apply to strain C and D. So strain C is located just below the neutral axis, while strain D is located just above the neutral axis. When the load is applied being upward direction, then strain C will naturally have tension and strain D will naturally have compression. Therefore, that's why the value of the strain C is going to have positive values and strain D will have negative values. So for the three axial strain gauge, which is for the E, F, and G, so for E, which is located 45 degrees upward from the x-axis, has the positive value, since once again the load is being applied upward, therefore it's going to have tension, and then the value will result in positive values. And for the G, in the other hand, it is 45 degrees downward from the x-axis, therefore it's going to compress when the load is applied vertically, and it results in negative value there. So lastly, we have a strain gauge F, which is placed on the neutral axis and is heading toward the x-axis direction. So as can be seen from the graph, it will have a minimum value, which in this case have negative magnitudes and is smaller than the other strain gauges value. So theoretically, the strain gauge which is placed on the neutral axis should experience zero strain, because the neutral axis is the location where tensile and compressive stress balance out. However, in this case, there is a negative value or non-zero value, which could indicate some errors, such as misalignment of the strain gauge, imperfect neutral axis location. So neutral axis might not be in the middle of the beam, where it could happen due to impurity. Also, strain gauge calibration could be the problem. And although it is non-zero, the value is very, very small. So I think the result is quite satisfactory. So moving on to the strain versus load graph of each of the strain gauge. So instead of plotting the strain in respect to time x-axis, we will plot it in respect to load x-axis. Yeah, and in this case, all of the strain values of the each strain gauge is linear in respect to the load, which is good. So in this experiment, we are using from 0 to 50 pounds load, and as can be seen, as the load is increasing from 0 to 10 to 20 to 30 to 40 until 50, the strain that is happening toward the beam is linearly proportional to the load. So moving on to the next section, which is we are obligated to calculate the moment of inertia of the beam. So since the beam is an I-beam, we can calculate its moment of inertia by first determining the dimension parameter of the cross-sectional area, which is as can be seen from the picture on the left and on the right. As can be seen that the upper and lower rectangular part of the beam is not the same from the picture and from the model. Therefore, we can only approximate the moment of inertia of the beam specimen here. So as can be seen from the next slide, which is the calculation. So we're going to be using the sigma I equals to the I of the whole square minus 2 times I of the small square. So we're using the formula of moment of inertia, bh to the power of third over 12 of the whole square minus 2 times bh to the power of third of 12, plug in the dimension, and we can get the moment of inertia, which is pretty accurate compared to the one found on the internet. So pretty happy with that. So moving on to the next session, where I'm going to be calculating the section modulus of the I-beam. So the formula for section of modulus is going to be moment of inertia divided by y, which is a distance from the neutral axis to the surface area of the beam, which is the very top part and the very bottom part. So it results in, as can be seen, the result is 0,000026694 meter to the power of third, since the moment of inertia is meter to the power of 4 and y is meter. Therefore, we get the result in meter to the power of cubic. So finding the moment of inertia and the section modulus of the beam is important, because later we're going to be wanting to calculate the Young's modulus of the I-beam, which is going to be obtained through experimental data, calculated through the experimental data, and then we're going to compare it to the theoretical data or references that's going to be found on the internet. And there are several formulas that are requiring moment of inertia and section of modulus, such as moment mc over I, and for the sigma stress, bending stress, which is m over s, we're going to need the section modulus. So it's important to find the moment of inertia and section modulus first. So moving on to the FBD, SFD, and BMD of the specimen. So since this specimen is a cantilever beam with an applied load going vertical at the edge of the beam, we can make the FBD such shown in the picture. So for the fixed support, we're going to have a moment at point A, and also a reaction force that is going to oppose the applied load. So the applied load here we denote it as P with a length L. After we construct the FBD, we can then continue to do some static equilibrium analysis. So from sigma moment at A equals 0, we can get that the moment at A is equals to the P times L. P is the applied load and L is the length of the beam. Since we're going to be using the applied load of 50 pounds, therefore converted is going to be 222.4 Newton times the length of the beam minus 0,735. So this is actually not the full length of the beam, rather it is the length from point A to the location of the strain gauge, because we want to find the stress that is located near the strain gauge. Therefore, we're going to use that length, and the moment resulting in 175.7 Newton meter. So here's the shear force diagram and bending moment diagram. Note that the length of the beam here and the shear force of the beam is just for visualization, so it's not true. So I'm going to be expanding here. Since the load is going vertical at the edge of the beam, at the end of the beam, therefore the reaction A at point A is going to be negative, and the reaction A, magnitude of the reaction A and the applied load is going to be the same. Therefore, the SFD will have like minus value at the start of the beam, going up until at the end of the beam it's going down to 0 again. And for the BMD itself, since the area of the SFD is negative, it's expected to have a downfall slope or a negative slope. So since there's clockwise moment at the at the point A at the start of the beam, we're going to count that, and the magnitude of the moment is going to be positive in the BMD, and after that it's going to be going down until it reaches 0, since the area of the SFT is negative. For the calculated Young's modulus, here we have sigma equals m over s, since we're going to want to account from the distance from the neutral axis to the surface area. So we use section modulus. Since s is equals to I over c and mc over I, we can substitute the c over I to the 1 over s. Yeah, so the moment we just calculated earlier, 175,7 Newton meter, plug in the section of modulus that we have calculated also earlier, it results in 6,58 MPa, the bending stress or the sigma. So since the formula of the Young's modulus is the stress over strain rate, we're going to have to find the strain rate first, which is can be calculated from the formula deformation of strain divided by the original length. So the deformation in 50 pounds of or 222,4 Newton, it is recorded to be 81,1 mu or micrometer, and is divided by the length from the start point to the strain gauge location, which is going to be 0,79 in this case, 1,525 minus 0,735, which is resulting in the strain rate of 0,00103. And plug that into the Young's modulus equation, we're going to be having a 64,1 GPa of Young's modulus of elastic, modulus of elastic. So yeah, so the error here is 7%, since it is found on the internet that the ideal value of the Young's modulus of the specimen is 68,9 GPa. So we're going to be calculating the shear modulus of the specimen by using the strain values given by the strain gauges and using tau, which is the shear stress, which is calculated by V over A. V we use 50 pounds. We're going to be using the strain and V data of 50 pounds, which is 222,4 Newton, and the area is the web area of the I-beam, which is the vertical rectangular part only of the Y-beam of the I-beam, since that's the one that's going to resist shear force on the beam. So tau equals V over A. V is 222,4, area is 387,75. Divide those two, we get 0,574 MPa for the tau stress. And for the gamma we can calculate gamma using 2 times epsilon 0b minus epsilon x plus epsilon y. So I'm assuming that the epsilon 0b is the strain gauge that is located in the middle or on the neutral axis, which is heading toward the x-axis direction, which is in this case the strain gauge F, which has the value of minus 6,41 strain mu. If I look it up on the data of the strain gauge, for the sigma x, I'm assuming it is E, which has the positive value, but the maximum or the 50 strain at 50 pounds being 15,87 mu. And for the epsilon y, I'm assuming that it is going to be strain gauge G, it's going to be minus 23,45 at 50 pounds. And using the formula that is provided on the lab module, we're going to have a gamma of minus 5,24 mu or micrometer. No, it's not micrometer, sorry, it's just mu. Gamma has no dimension, has no unit, is dimensionless. So calculating the shear modulus of G equals tau over gamma. Tau is 0,574 MPa divided by minus 5,24 times 10 to the power of minus 6. We get the minus 109,5 GPa, which is totally in the result has a very low accuracy with respect to the shear modulus gotten from the internet, which is around 26 GPa. I think this can be caused by the formula of the gamma itself, since it is required to insert epsilon x and epsilon y. So epsilon y, unfortunately, in the triaxial strain gauge that we put in the middle of the beam, there is no strain gauge that is heading directly toward the y direction. Therefore, I'm using in this case is the strain gauge that is heading toward the downward direction of 45 degrees respect to x-axis. Therefore, the value might not be so accurate, and yeah, leading to the inaccurate answer. So moving on to number 10, where I'm going to be discussing the theoretical strain gauge of A until D and discussing it with the experimental one. So let me talk about the formula on how to get the strain first. So first of all, we're going to be calculating the theoretical stress for the strain A until D first. So basically sigma equals mc over I, where the C for A and B is 0,04, since it's from the neutral axis to the surface area of the beam, while the C for the strain gauge C and D is going to use 0,02 meter, since it's from the neutral axis to just slightly above and below part of the neutral axis. And the I that we're going to be using here is found on the internet to maximizing the accuracy of the strain, or the theoretical strain. And after we get the bending stress from the mc over I, we're going to use the formula epsilon equals to the bending stress over Young's modulus to get the epsilon itself. So using the bending stress that we've calculated earlier, and then using the Young's modulus that is gotten from the internet, which is 68,9 GPa, we'll be able to find the theoretical strain for A and B, and also for C and D. So for A, the value is going to be all negative, for B is positive, for C is negative, and for D is positive. I'm sorry, C is positive and D is negative. So the magnitude is the same, since the placement with respect to neutral axis of each of the strain gauge is basically the same. It's just one is on the upper part of the neutral axis and one is on the bottom part of the neutral axis. So after having done to calculate the theoretical strain of the strain gauge A to D, we're going to have to plot the graph, strain versus load graph of the theoretical and experimental value of the strain, and then compare them with each other. So as can be concluded from the four graphs, it is clear that the theoretical value of the strain gauge A until D is relatively bigger than the experimental, whether it is compressive or in tensile. The cause of this discrepancy is maybe because of the strain gauge's calibration might not perfectly match the material's behavior. Therefore, it might not be zero initially. Therefore, can lead to these discrepancies. So also there's a possibility of material properties variations. So the actual Young's modulus and also moment of inertia of the specimen that is on the lab is not exactly the same as the one that is found on the internet or from literature research. It's not the same. Therefore, we cannot really use the theoretical one. We have to calculate the Young's modulus and moment of inertia and all that based on our result on the lab.